I know this may be a little overkill, but I want you to become very familiar with the calculation of variance under different conditions. So if we have a case where we have 6 measurements or items that we're collecting data for, and let's pretend that these are the 6 values that we've collected from each subject in a population or a group of measures that we're performing. The first step for calculating variance, where I have a group of 6 objects and I have measured each and every one of the 6 objects exclusively, all of them, each one, the whole set. Everybody with me?
Yeah.
Okay. So it's just a different representation of what we reviewed in our last session, but let's pretend I have 6 values. The first thing I calculate is what? What does this represent here?
Percentage?
It's not the percentage.
No, wait.
I have these 6 values and I'm doing something to them, and I get this number and I'm dividing by 6.
Oh, the what is it called?
Average.
Average. Average.
The average, yes. Yes.
Yeah.
Yes, good. Good. Okay. So we want to take a look at this with different representations of the same process, right? So that you're walking through this on a deeper level. Okay. So the first step is to calculate the average for all the items in that set of measures or items in a group. And in this case, I have 6 items total and I'm measuring all of them. And so I get an average and I have that number 35. What do I do with this number 35 to perform the next step? I do something with the original numbers and I use this number with the original numbers. What am I doing next? I'll give you a hint. What is this?
We're running a formula through them, right?
Yeah, basically you're taking that average and then I'm subtracting the original value of each number to figure out the difference. So I take each number, I get the average. Then I take the average and I find out, okay, if this is the average, how different is each value compared to the average? So I'm calculating the difference between the average and each value. That's the second step, okay? That's the second step. That's what's represented by this chicken scratch right here, okay? So 35 minus 10, 35 minus 20, 35 minus 30, then I have 40 minus 35, 50 minus 35, 60 minus 35. And I get a number, and then I square that number. That's the third step. So I calculate the difference between the average and the original values, and I get a number for each of those. So 25 squared, what does that equal? 625. What's 15 squared? See, I took 20 minus 35, then I took 30, 35 minus 30, and then I took 40 minus 35, 50 minus 35, and 60 minus 35. And I got each of these values, 25, 15, 5, 5 again, 15 again, 25 again. I square those, right? When I square them, it gives me these numbers. So 25 squared is 625, 15 squared is 225, 5 squared is 25, 5 squared is 25, 15 squared is 225, and 25 squared is 625. All right. Now I divide by the number of values again. If I add all these together, I get 1750, and I divide by 6. Now, that gives me variance. It gives me a variance of 291. Yes, in our last session, I said, but let's take a different case. Let's say I'm calculating variance for a sample of values. I have a huge number of subjects to measure. I don't have the time to measure them all. I can't work calculations for all of them. I'm going to randomly select 6 items out of a very large group of subjects, right? So I'm doing 6 measures from a very large population of possible subjects. And I want the variance as well. What am I going to do in this last step to make sure I have a valid result for variance, where I'm calculating variance on a sample instead of all the subjects? I'll give you a hint. It has to do with this number right here.
Repeat the question.
All right, so now I have the variance. I've calculated the variance for a case where I have 6 items total, and I measure all 6. And then I get the average of the values for those 6 items. And then I go back and figure out the differences between the average and those original values. And then I square the difference. I square the difference between the average and the original values.
Uh-huh.
I add them up again, and I divide by 6, and that gives me my variance. That's for a case where I have just 6 items, and I'm able to measure every one of them. And my measurements yield 10, 20, 30, 40, 50, 60, right? So now I said, how is it different if instead I'm performing variance calculations for a sample, a small subset of items? Let's say I have 500 possible subjects, and I only have time to measure 6. So now, instead of measuring every one of them 500 different ways and calculating variance with 500 different values, I only have time for a sample. This is real life scientific method, right? Real life scientific computing. I don't have an unlimited budget. My lab assistant wants to go home and enjoy a date on a Saturday night. So my lab assistant is not going to sit there and measure 500 different samples. Are you with me?
Yeah.
Your lab assistant says, hey, we can still calculate variance using a sample. Let's just randomly pick 6 of these and measure them. So now the situation is different. Instead of measuring all of the subjects, I'm only measuring 6 out of the sample as a sample of the 500. I perform the exact same steps to calculate variance, except when I get to the end here. What am I doing differently right here? Do I divide by
Squaring?
6?
No, it should be 6.
I can't divide by 6, I have to divide by 1 less. Because I'm using a sample, I don't divide by 6 if the denominator, if the number of samples that were measured is 6, if that's n number of samples is 6, then I have to divide by n minus 1. Whatever the number of samples I'm using to calculate variance, when I get to this piece right here, instead of dividing by 6 here, I divide by 5 instead. So I put 1750 and I divide by 5. My variance is 350 instead of 291. Okay? Does everybody understand what I just did there?
Mhm.
Now, you get a very different answer. 350 is a very different answer from 291. Can everybody understand what I'm saying here?
Yeah.
This is a very basic descriptive statistical method. And you have to be able to calculate variance accurately, whether you have captured measurements or inputs for each item in a group, or if you only have time for a sample. And that one difference makes a huge difference, right? That one little piece of it. Now, to get standard deviation, all you do is take the square root of your variance. So in order to calculate your standard deviation, if we had only 6 items to measure, and that was all there was to work with, we would divide by 6, we'd get an answer of 291 for our variance, we'd take the square root of 291 and we'd get 17.06. And that little squiggle has to do with significant numbers, right? Significant figures about that. So I'm not 17.06. That's my standard deviation, which means that when I'm looking at how values are distributed on a graph, I can tell how much of a percent of those items fall into which distributions. So patterns of data points, the distribution of data points, if you can pick up on patterns in the distribution of data points, you can identify relationships, draw informed conclusions about things and all that, right? What happens if you don't have a complete measure of everything and you're only using a sample? We go back to this and we have 1750 and we divide by 5 instead. So if we're using a sample, we get a different variance. Now I'm going to take the square root of that. If I round up to 2 decimal places, that's 71. 18.71 as opposed to 17.06. Now that may not seem like a big difference, but it does mean that the distribution is going to be different on that bell curve. So I wanted you to see this another time with a different representation, and I wanted to walk through this one more time again, because basically there's a lot of simple mistakes that are made when people start working simple calculations and basic statistics. And then when somebody finds out, no, that's wrong, and all your stuff is wrong, because it's one step, it kind of dampens everyone's enthusiasm for the use of statistics, right? This is one of those areas where people trip up a lot, but the difference in the outcome, the difference in the output is significant. So they don't get reliable results and then they're left scratching their heads. And it is a very little thing. So anyway, there you have it. I've walked through it again. I just wanted to make sure that we understood. First step, get an average. Second step, determine the differences between each value and the average. That's what we did right here in the fine print. Then I take that.
Okay, so to sum it up, minus it by the average and square it.
Yes. You're squaring the difference between the value and the average. So in this case, I had 10. In the next value, I had 20. In the third value, I had 30, 40, 50, and 60. So 35 minus 10 is 25. 35 minus 20 is 15. 35 minus 30 is 5. I take each of those numbers and I square them. 25 squared gives me 625. 15 squared gives me 225. I add all those together and then I divide by 6. That gives me my variance. Only in the case where I am measuring or collecting data for all the items in a set. If I'm not, if I'm only sampling, I divide by 1 less, which gives me a different variance, which gives me a different standard deviation. You have to know how to do variance accurately under different cases in order to get correct standard deviation under different cases. That's how a standard deviation of a sample can be accurate, even though you're not measuring everything, which is like significant, okay? That's a big thing. That's why we're taking the time to walk through it. Any questions about what we've just covered for standard deviation and variance under 2 different cases? Sampling is a data-centric activity or process to ensure appropriate qualification and consistent collection of selected data. Ideally, when you're sampling, the more random your sample, the more valid the sample. Let me say that again. The larger the pool of data and the more random the sample, the more valid the sample is considered to be. So you have massively large data sets that are simply collected and used repeatedly for all sorts of studies. So in your Monte Carlo simulation, you're using the fill down option like we did for kinetic energy. You're going to use that same feature, only you'll use it with a couple of extra steps to generate random numbers in a very long series of values. And then you're going to capture that information and use it to calculate a Monte Carlo simulation. So this is where you just walk through the example. That's where we get to this idea about massively large data sets. So oftentimes, if you generate random numbers, you can use that large set of random numbers to calculate in advance, what if scenarios. And that's what simulations are all about. And that's Monte Carlo is a simulation method. So depending on the nature of the study, data elements may be sampled giving a specific criteria. So you may filter a set, maybe the sampling is defined within certain parameters. So you can have data that you're analyzing and you can say, well, let's see what it's like for all the males. Let's see what it's like for all the females. That gets back to sorting, right? That gets back to those relational algebra operators. Which one is it that filters, by zip code and so on? It's okay if your sampling is focused based on a criteria or 2. In fact, that's where a lot of conclusions can be drawn. Oh, for males, our results are very different than for females, which could signify or mean that, there's something specific about relationship that impacts only males as opposed to females or vice versa. So there are times where you select the data and you filter it and you only use a certain classification of records. In other cases, you're not selecting anything. It's completely random and there's no partiality or bias for a given study. You want to be able to qualify what it is your calculations represent. So if there's selection in your outcomes, you need to state for males of a certain age range or body mass. So when it comes to sampling and filtering a sample, that's something that's easier to understand if you've had a chance to walk through an example, which is why we have our assignments the way we do. In such cases, the more authentic the random selection, the greater the level of confidence may be claimed for outcomes. Now, it's kind of a holy grail for mathematicians to devise an algorithm that generates truly random output. This has been, when I say holy grail, usually when you use random number generators in software, those random number generators are not truly random. The way the algorithm is written actually creates a pattern of variability that's, if you analyze it enough, is pretty predictable. So put another way, if you artificially generate random numbers using a computer with an algorithm that cycles through a series of calculations, depending on the computer, it's not as random as you might think. So computer-generated simulations are limited in their accuracy. Well, what's the workaround? There is a workaround. You can use, you can combine natural data with computer-generated data, and that'll give you a better set of random numbers, authentically random numbers, to work with for artificial simulations, right? So here's an example. There are supercomputers. There are supercomputers that are tasked to generate random number sets. Why? Because random number sets that are truly random are like the raw material that simulations use to artificially calculate what if scenarios. So, what is the importance of random numbers in computers? Random numbers are critical for lotteries, complex mathematical modeling, for gambling, for cryptography, for security. It is a holy grail. There's a lot of effort being devoted in mathematics research to coming up with a better way to generate random numbers. If you take audio noise from sound samples, like, anybody here have a fan that has like a annoying clacking, clicking noise? When the fan runs, it's got like a brrr kind of a noise in the background.
Yeah, it does that sometimes.
Or has anybody ever recorded the sound of waves on the shore by the ocean? So you like the sound of waves, it helps you go to sleep. That's called white noise, right? So if you record crashing waves, you can perform a calculation where the digital recording of that noise is combined with a random set of numbers. And what you get is better randomness in the numbers. So this is one thing they're experimenting with now. They're mixing, or it's called seeding. You can take a basic set of randomly generated numbers with random functions in software or in a spreadsheet, and then you can combine it with some other code to infuse the noise into the random numbers. I guess that's, so you can basically generate random numbers from white noise. You can perform calculations that use the random numbers with other random natural data, like, you know, ocean waves. And that gives you a better outcome of random numbers. And the better the random number set, the better your simulations, or the more accurate your simulations are. Okay. So whenever you're performing statistical calculations and you want to use different samples and you want to run different trials, you just get better outcomes. So that was something I wanted to explain a little further in our study guide.
Excuse me, Professor Kenta.
Uh-huh.
This is James. I just wanted to say sorry for being late. I had a little issue with some baby turtles hatching where I live. So,
Oh, well, I understand, and I hope you're helping the baby
You're
turtle.
lucky.
yeah, we found the mother. She got ate by a shark. So we were trying to move the baby out of the way. So
Did you
Oh.
call the Did you call the Sandy Point Reserve, the people that work at Sandy Point?
it wasn't by Sandy Point. It was down by Princess.
No, you can
Huh.
like call them and they will actually come and assist and pick up the turtles.
Oh well, yeah, we did call DPNR and they said to call some. So we were
Yeah,
just moving them.
Yeah,
Wow.
you usually would be called like C.
So you're saying that there were baby turtles, but one of the mother turtles was eaten by a shark.
Yes.
Which one was it? Was it like were they hawksbills or leatherback?
Leatherback.
Mm. Wow.
Oh
There's 3
man.
patches of eggs left, and one of them hatched right next to where I am. So I was kind
Oh,
of
man.
left in the sand.
Well,
Lucky, but that is sad.
I'm glad that something good came out of a bad circumstance. So yeah, glad you can join us in progress. We were just talking about using different sampling methods with raw data or random data for simulations. So one of the essential components of computer simulations and modeling, the ability to work modeling, is to have raw data or random data to use for the calculations. One last topic we'd like to cover in our class before we close out today and just share screens to assist with assignments or solutions is this new trend of data analysis called NoSQL. So your solution involving data mining is based on structured query language, and we're using normalized data sets. So we have structured data that's intentionally organized in order to be able to perform, you know, data analysis. So we can pick up on patterns. We can identify relationships between data elements and data sets. The thing that we'd like to impress on you today is that there's a new movement and this has only been around for about 10 years, where they've realized a lot of the data that they want to collect and analyze is not organized. It's not cleanly arranged so that you can work relationships or joins between those sets of data elements. And that poses a huge problem. Now, one thing you can do when you collect data that doesn't have a consistent format is you can manually or artificially perform cleanup on the data. So, and this is very common, is that data is collected. A great example of this would be to run some quick code to capture the code on a website, right? Where's the view source code option? Does everybody know what I'm talking about? Computer science folks?
Source code, source code.
Everybody see this?
Yeah,
Okay. So let's pretend that we have an algorithm that's going to execute a view page source command. Wow. Now, if I line wrap, that might help in terms of readability, or it might not. So this is the source code of what we were just viewing. Let's do that again. Okay. Why is randomness and why is it so important? We're looking at this. Oh, let's view the source code for a new Google prompt. I just want to view the HTML source code for this screen, something people see all the time. Now I have bookmarks up here, so I have shortcuts for my frequent interests, right? And you see, based on my searches, Google is figuring, oh, these are some things I'm probably used to, because I'm always into my cell phone service or my electronic textbooks and so on. So everybody's is going to be a little different. Everybody's web page is going to be a little different. But let's say you're performing a study and you want to perform an analysis of everybody's Google splash screen, right? So you view the page source. Well, that's simpler, isn't it? Compared to this. Wow, what a difference. Well, let's line wrap it just to make sure. So if we feed a little bit of information into Google and we get a listing, and I don't want to view the source code. So maybe, well, there's no going back, is there? Can I just reload it? No. No, I kind of have to go back to this. And what a difference between this information. So I have a few words. What is randomness and why is it so important? Now, obviously, Google has a lot of artificially intelligent algorithms that are designed to interpret. I mean, Google is aware of my interests, my personal interests. And when I pose a question, if it's Professor Kentop that's asking this question and it's somebody in, I'm trying to think of a scenario. It's somebody in another country with a different language and their interest in randomness is about gambling or something like that. Well, Google knows that this person is interested more with randomness because they want to figure out how to beat the casino and cheat at gambling. So essentially, when Google operates, it's going to cross-reference those interests with these keywords like randomness, right? And why is it so important? When I type that same question, because my purpose about randomness is academic and I'm teaching, computing methods, it's going to give me a different result And so what I get on my Google output is going to be very different than somebody who wants to figure out how to win at a casino, even though we both have the same interest in randomness. The point I'm trying to make is that we take for granted how complex the information is and the mix of information. And if we try to study that in a meaningful way, and I take just my splash page before I enter any terms into it, and I view the source code, it's a pretty straightforward result. But if I do that for you, there could be some significant differences. So what do we do if we're trying to perform data analysis for online sources of data or data that's in different formats? This is where the NoSQL movement has come in. So open source data may be readily accessible, so you can often get it by viewing source code, or you can do something called a screen grab. You can copy and paste information, and it's called screen scraping. So if you get data on a screen and it's not in a data file, you can copy and paste it into a text editor, and that's called screen scraping. What you end up with is a lot of different types of data, garbage in, garbage out. This is a big problem. It's great if you understand how to organize your data up front, and then you can glean all sorts of useful information from it. But most often, the data that's readily available to us, it's not organized. It hasn't been intentionally organized in a specific format. And because of that, there are tools now that allow you to take big chunks of data and dump it into a NoSQL resource like JSON or BSON. They have all these new databases called MongoDB and HBase. There's one called Hadoop. One of the most well-known is called Splunk, right? So these are NoSQL data analysis methods. So to give you an idea of how this would work, what are some cool features? Let's change this, Splunk features. So basically, if you dump a bunch of different data types into Splunk, what Splunk will do is it'll parse out, or it'll pick out a lot of common elements. So this isn't a bad review here. What are some of the best features and use cases for Splunk? So system logs are a great example of some work in computing applications where we're losing the war. Hackers are getting in on our systems. And if we take a look at our system log, if we go to manage our computer in Windows, and then we look at the event log, our Windows log, there are things in our system log that would correlate or connect with our security log. Things that happen on our system after there's an event, a security event. So here you see some examples of the data that the Windows event log stores for security events. And if I pick a security event, like a logon, I can basically view this in a different format or in its native format, where it's in XML. Okay, and XML is a kind of hypertext language, and when I'm putting it through a viewer, it helps format the content, much like HTML is used to format web pages. To make a long story short, there's a lot of information that we want to see, and so this is the raw data in a friendly view. This is how it's actually stored. This is how it renders to the screen when I'm viewing it, right? So it's kind of parsed out and organized like a web page, so I can see different categories and such. Well, if I want to collect security events, and then I want to collect system events, oh, here's something right here, right? I have a warning. And so there might be some data elements in my system log that I'd like to see if that same element appears in my security log. Does everybody follow what I'm saying here? Let's pretend that I have a format where I'm collecting data about events that are happening on my system. Okay, like this warning. There's a warning here. And I want to see if there's any connection with events in my security log. When I look at my security log, even if I correlate the same time and date and all this, oh, here's something about a special logon. Does that have anything to do with the other error, the other problem in my other log? Those are hard dots to connect. And this is where NoSQL tools and platforms like Splunk and Hadoop and MongoDB are really breaking new ground, because the more we digitize everything. Has anyone ever heard of the Internet of Things? The Internet of Things? Anyone? Internet of Things?
Yeah, the thing that basically is the internet in its entirety.
Not really.
Oh, so it's not that song, Welcome to the Internet?
It may be related to that. The Internet of Things is a term that's used to describe how more and more devices we purchase, more and more items we buy, they're smart devices that connect to the network, right? Can you think
Oh,
of
is this where like when you purchase an item and then is this where you purchase an item or mention something and then for some reason it instantly comes up as like an ad?
no, that's not the connection here that we're going for, but the Google thing we were just talking about does. So when you have things you do online and web screens, Google is tracking everything you do. Facebook is tracking everything you do. Twitter is tracking everything you do. Your cell phone provider is tracking everything you do. Why? Well, they're using data analysis tools so that when you search for things, they want to put information and options for your consideration in front of you. That's why you get ads, right? The people who are selling goods and services want to have a better way of presenting their goods and wares in front of consumers. But this becomes really, we're going to reach a tipping point soon. So one of the things that's happening right now is that the Internet of Things, all right, and yes, there's a lot of confusion over what an Internet of Things, not to be confused with the Web of Things, right? Like the World Wide Web. That's all web pages. The Internet of Things describes physical objects with sensors. So in your house, right now, when you bought a speaker to listen to music in your house 20 years ago, could you connect it to your internet wirelessly? Yes or no?
No.
No, not really. You could connect it with a cable to something that played the music, right? That's what you could do 20 years ago. You could buy a speaker that was nothing but a speaker, and it had a cable, and you could plug it into a tape recorder or a Sony Walkman or an iPod or an MP3 player or a stereo, but you'd have to connect it with a wire. And the speaker could only do what you're supposed to do with a speaker. Now I can buy a speaker that connects through my Bluetooth and through my wireless to my smartphone, to a tablet, to a PC, to an entertainment system, to a stereo, because those things have sensors and they have connectivity. These are smart devices that are connected to the internet. It's estimated that there will be 50 billion Internet of Things devices that are connected to the internet. Now, I just gave you an example of the logs that I get on my laptop. So here I am in Windows, and my Windows logs, I can see what's going on with my software in an application log. I can look at a security log to see if somebody's trying to break into my laptop. I can look at a system log to see if my system components are healthy or if there's something weird going on with them. Like my system could be saying, "Ooh, you're sending a lot of data out of your Wi-Fi port. What's going on here?" And then on a related note, the security can say, "Hey, why is somebody reading all of your music and movies? And why is that information going out over the internet?" Put another way, Windows has a way of capturing all the data about my laptop activity in a certain format, which could include XML. Oh, hey, look, that information, that specific piece of information is about how some information is encoded so that it can be formatted, so that it can be viewed in a sensible manner. But that format is a problem because when you try to, you can't connect different XML files the way you can connect different data tables. When you're doing your data mining solution, you're using Access and you're using a set of data tables we've already built before and we've already talked about before, and the data is organized. But what do you think happens when we're trying to study data and all of a sudden I have an intelligent personal entertainment speaker like JBL? What's the most popular speaker that people like to use now with their smartphones? Quick, anybody? Favorite brand?
Speak-
JBL.
JBL. It's a good
Yeah,
example.
JBL.
I have
Yeah,
a
I remember JBL.
yeah, Sony makes them, JBL makes them, a whole variety of Bose has a standalone speaker, right? There's all these companies. Beats, there's all these different companies that make smart speakers. You call them smart speakers because there's a processor in there. Did you know that you can talk on the phone through your speaker when it's connected to your smartphone? Like, like you can talk through your car stereo, which is tied through your smartphone to your cellular provider. People do that now, right? Well, guess what? The connected car is a thing that's on the internet. The smartphone that's connected through your car is an internet. It's an internet of things, right? It's part of that whole population of devices. Embedded systems, wireless sensor networks, you have personal assistants like Alexa. And the moment I just said Alexa, I have a Fire TV. And that stupid remote is sitting 6 feet from me right now. And when I say Alexa, the audio turns up and it starts paying attention to what I'm saying. So if I say, Alexa, power on my smart TV, that crazy thing will start interacting, right? Well, here's the problem. In just a few more years, in less than 10 years, it's estimated that there will be 50 billion, not million, billion, 50 billion devices that are connected to the internet, that are intelligent, that are all a part of the internet, the network, right? And all of them have exposures. All of them can be hacked. All of them have some kind of log. And the simple truth is, if I want to find out how somebody is hacking my laptop through my smartphone, because that's already happened, how somebody is hacking my laptop through my smart TV, my flat screen TV. It's already happened. How somebody is hacking my laptop through my wireless router. It's already happened. The wireless router, the flat screen TV, the portable speaker, all of that, my smartphone, they have logs, and those logs are tracking certain details, but they're all in a different format. I can't just suck them into an Access database and find out, okay, here I have something that's going on in my system. Which security event is related? I can't do that. And that's a huge problem. Data scientists have come up with this new classification of tools, right? And so I want you to memorize these: JSON, BSON, or binary JSON. So binary JSON is ones and zeros. XML, YAML, HBase, MongoDBase, Redis, Cassandra, Couchbase, Hadoop, Splunk. These are all tools that are capable of sucking in different kinds of formatted information and then analyzing them to see if there are common elements or characters in the mix, right? So this is one of those things that data science is taking seriously, and there are some very bright people in the mix that are working new methods for data analysis when there is no structure to the data. There is no format to the data. The point I'm trying to impress on you now is you can spend half a lifetime trying to capture this information in a friendly view or in an XML view, and you can try to analyze it by cleaning up that format and then building a data set that you can relate. But you would likely have grandchildren by the time you figured out how to do that. The kind of stuff that we're doing with data mining using a SQL database is time-honored and it works, but you have to structure your data tables. You have to design your data tables up front. And the amount of information you can get out of there is limited by the design of your data tables and how they're related. Let me say that again. The amount of useful information you can get out of those data tables is limited by how well those tables are organized and how you choose to relate them with joins and with relationships. What we're finding is that the world is getting so digital, so fast, and there's so much information, we can't perform data analysis well without different tools. That's the whole point of this last section. It's a very short section, but I wanted to spend some quality time explaining what the heck this means. Because the future in data science ahead, and for much of scientific computing, is going to involve methods of data analysis where we don't have a clean, organized format. Okay? Now, that was all that I had planned to cover out of our study guide. There are some additional references for you to consider. That's it for our review. you can count on me trying to trick you in your module assessment by mixing up the different methods. Like I'll say, okay, which of these is not a NoSQL method of data analysis for free-form data? Free-form meaning, okay, it's a different format in each case. You got all this data, but each of the records is in a different format. Like you were trying to look at the security logs for a wireless router, for a flat screen TV, for a portable speaker, for your smartphone, for your tablet, for your car, right? Your satellite dish, all those things. What would you use? Which of these might be a good tool or a resource to use to analyze data from all these different kinds of data types? And I'll throw in something like this. And you'll say, no, Monte Carlo, that's a simulation method that is designed to create predictions based on random number sets, right? And so simulation models include, but are not limited to, antithetic and control variates, PRNG seeding, importance sampling, Monte Carlo. You're actually performing the Monte Carlo in the first solution, right? So I may ask you a question and then throw in something about a NoSQL method down here. And you have to understand the context. This one's about simulations with random numbers, right? It's a simulation and modeling method. This has everything to do with data analysis where none of the data samples have a common format, and but there's still something to connect the dots with, right? When I look at my system log, I know there's a connection between what's happening on my system and the security events that are happening on my system. But I'll be darned if I have a simple way to connect the dots. That's where we're headed with NoSQL, okay? Any questions about what we just covered? Well, thank you.
No, just looking forward to seeing the recording so I can review again.
Okay. I will